And then whatever you need to use your calculator for, use your calculator for. But you really want to make sure you have all your perfect squares memorized. Which is essentially just knowing times tables, right? Oops, see? What happened there? Okay, and at least up to 5 cubed. So 2 cubed, 8, 3 cubed, 7. You guys are using your, whoop. What's going on? 27. Hello. It's not good when something works and then doesn't work all of a sudden. That's not good. Oh, there it is. Weird. 4 cubed is 64. Let's erase all that. 5 cubed, 125. Does anyone know 6 cubed? Well, I guess you probably don't now. 216. 7 cubed, 343. 8 cubed is 512. You might have heard of for storage devices, they used to be 512 megabytes. No? Now they're just like a lot larger than that. That used to be like 128, right? They're all power 2s. 9 cubed, 729. And then 1,000, that's the easiest one. 11 cubed, 1331, and then 1728. Okay, I guess you should also know 10 cubed. That one kind of comes up every once in a while. And then, of course, all your perfect squares, and at least up to 5 cubed. If you have those memorized, you usually cover all your ground for looking for the largest perfect square, perfect cube factor. The stuff on the front is just review. You should know, like, this little number is called the index, right? If we don't have a number there, it's going to be an index of 2, right? A square root. So if you don't see a little number, the index is 2. So we don't really write the 2 for a square root. It's kind of a waste of time. If there's no coefficient, it's a 1. Some basic stuff like that. And then some property of radicals that you learned about last year. For sure, the first one, root A times root B is root A times B. That only works if it's the same index. So you can't combine a square root with a cube root. It's like trying to combine the third dimension with the second dimension. They're not the same. They are not compatible. The same goes with division. If you root A over root B, it's the same thing as root A over B. You put them under the same radical, and we'll be using that in the next couple days as well. All right, so just some properties. Here, root A divided by root C, the A's can just cancel out, essentially, because we can put them all under one square root, and then A's cancel. So root B over C. Okay, so how do we simplify this? Let's talk about converting into entire radicals. It's not very common that we ask you to convert something to an entire radical. The main purpose, The
class dummy is here to get comfortable.
Just get comfortable with what you're comfortable with. Okay, so the main purpose is for ordering. It's not the most simplified. So entire radicals are not simplified. Okay, it's the opposite of simplified. We usually do it so we can order the radicals. So for example, if I had like 2 root 6 and 3 root 5, which one's larger? Well, by changing them into entire radicals, I easily see which one's larger, right? Do you remember how to change this to an entire? Well, square the 2, right? Raise the coefficient to the power of the index. So if we're comparing, 2 root 6 and 3 root 5, this would be square the 2, which is what 2 squared is, 4, and then multiply it by the 6, which gives you 24. Okay, so to bring the 3 inside, I would have to do what to the 3? Square it. Raise it to the power of the index, which is 2. So 9 times 5. So who is larger? Clearly 3 root 5. So for ordering purposes, that's why we do entire radicals. So really quickly, we'll do a few of these. Oh, well, 2 root 6 we already did. Okay. Can you bring the negative inside a square root? No. So we're going to leave the negative on the outside, but we want to bring the 4 inside. So if I'm bringing the 4 inside, what do I do to the power of 4? 16 times 5, and 16 times 5 is 80. Leave the negative on the outside. Okay. Can we make 15 into an entire radical? Just square it. What's 15 squared? It's 225. So therefore, 15 is equal to the square root of 225. That would be your answer. Root 225. It turns out it's a perfect square, right? You could write 4 as an entire radical. You'd write it as root 16. You probably normally wouldn't. All right, what about a variable? Okay, we're going to square it to bring it inside. We're going to square both of them. So the 9 and the m, we want to raise to the power of 2 before we multiply it by 21. 9 squared, what does that turn into? 81. M squared, well, is m squared. And what is 81 times 21? That's a large number. 1,701 m squared. I'm going to zoom in more. Make this really large. There you are. Okay, this guy. So it's still a square root. So to bring him inside the square root, what do I have to do to 3 over 2a? You have to raise it to the power of what? 2 to square it. Right, to bring it inside, we're going to need to square it, and then we can multiply it by the a to a. So let's simplify that. This is exponent laws, first unit of grade 10. It's been a while, though, especially if it was first semester. 3 squared, 9 divided by 4 and a squared. We square everybody. If we're going to square an expression like that, you square everything that's inside, you're going to square it. Times 8a. 8a is a fraction. How could I write that as a fraction? Over 1. And how do we multiply fractions? Straight across. We'll simplify it after. So it gives me 9 times 8. 72a divided by 4a squared. Does 4 go into 72? Yep, sure does. Now, if you wanted to, you actually could have simplified earlier. You could have reduced the 8 and the 4 here and made this a 2 and 1. You could have done that as well. And then the a's can reduce as well. So you're welcome to do that. So it should give you 18. 72 divided by 4 is 18. And then what happens with our a's? If we have 1 a on the numerator and 2 a's in the denominator, one of them cancels and we're left with 1 a where? 1 cancels from each. There's 1 a left on the bottom. Yeah, because you have essentially a over a squared is the same thing as a over a times a. And so one of the a's cancel. We're just left with 1 a on the bottom. Okay? All right. This guy, what's the difference? You have to cube it. So let's cube it. A over, do you have to write the 1? No. A over 2 to the power of 3 times 80a, or a cubed divided by, what's 2 cubed? 8. So knowing those perfect cubes is very helpful. Times 80a. So if you want, we can go straight across, or we can go straight to simplifying this. Because 80 is the same thing as 80 over. It's just going to equal 10, right? Because this is 80 over 1. And the 8 divided by 80 gives you a 10. So we can reduce that to 10 and 1 if you want. And a cubed times a to the what? 4. We add the exponents, right? When we're multiplying, there's a 3 a's, and then add another a to that. You now have 4 a's. Do you want to try? You try the last one. G. So it is a cubic root. So you have to cube it to bring it in. What's 2 cubed? 8. What is k squared to the power of power of 3? K to the power of what? 6. Why 6? Power to about power? Because if you have if it's cubed, right, you have k squared times k squared times k squared. So that's why. Oh, that's not an eraser. Times 4k, which gives us 32 k to the 7. So if you got that, good job. So that's the easy part. Making entire radicals are easy because you don't really have to think too much. You don't have to break anything down or find products. You just have to raise it to the power of the index and then take that and multiply it by the radicand, what's already inside. Pretty simple. So we're going to spend a little bit more time today on simplifying radicals. So making an entire into a mixed. This is simplified form. And that's usually what you see. And you've already had some practice, right? We had some practice with quadratic formula. We had some practice in trigonometry. We're going to make it a little bit more interesting today. So these guys you should be able to do, right? For sure, A and B. Can you simplify A and B? Do you want to do one together? I guess I'll do one with you. So what's my process for figuring out how to simplify root 75? Find a perfect square. Now, if I'm not sure of my perfect squares, you can cheat a little bit. I mean, you should probably know your perfect squares by the time you're in grade 11. But you're stressed out maybe, it's the middle of a test, whatever. You can use the chart, and I think I've showed you this before. No? Maybe your grade 10 teacher did. We could type in x squared, so y equals x squared, and then go second table. We want to go to the graph, so second table. And so here in blue, which you can hardly see, I need to set up my keyboard again to make this bigger. But you can see your perfect squares, 0 squared, 1 squared. We want to find the largest one of those blue numbers, or largest perfect square, that is a factor of 75, that will divide into 75. So looking at these numbers right here, these are the numbers. What's the largest one that will go into 75? So if you're not sure, you can literally start dividing. So start at numbers smaller than it. Obviously, it has to be at least half as small. So you don't even have to start at 64. So 40. Like, knowing your numbers and not having number sense, this should be logical to you. If you don't have number sense, then you're going to start aimlessly typing in your perfect squares. What was the next one? I'm so sorry. Going backwards. 64, 49, 36, thank you. Prego brain or something. Okay, so 25 times 3, right? 3/4 is the largest perfect square. So 25 times 3 And then what are you going to do from, and you can write it this way, or you could also write it as root 25 times root 3. It's the same thing. Both are equivalent. Okay, you can split it up into two different radicals. And I'm going to start doing that more. What is the square root of 25? It's just 5. And so 5 becomes the coefficient. Right, so we try 80. And the largest perfect square. So notice I always go backwards. If you're actually searching with your calculator and start dividing, I go backwards because you want the largest one. Often there's more than one perfect square, especially like a number like 80. So you want to go backwards so you find the largest one. So you can start dividing by your perfect squares if you want. Should find it. Okay. There's two perfect squares that will go into it, both 80 and or 16 and 4. But which one do we want? 16. We want the largest so that we can be fully simplified. So square root of 16 times 5, or root 16 times root 5, which becomes 4 root 5. On a side note, if you did choose 4, so you broke it into root 4 times root 20, or 2 root 20, can you simplify 20 further? Is 20 fully simplified? So the question is there a perfect square that will divide into 20? Yeah, so it's not fully simplified. What perfect square goes into 20? 4. So you can break that down even further. And square root of 4 is 2, so it turns into 2 times root 5, or 4 root 5. So if you did, you know it's fully simplified if the radicand is not divisible by a perfect square. It's not divisible, then we're done. See, 20 is still divisible by 4, so we weren't done. See much longer if you don't choose the largest one? It's a lot quicker if you choose the largest. So 54 is this, it's already mixed, but is it fully simplified? No. What perfect square goes into 54? 9. 9 times 6. And what is the square root of 9? 3. So it turns into 2 times 3 times root 6. Right? The operation between all three of these is multiplication. And so it actually turns into a 6 root 6. 2 times 3. Okay? All right. So this is what you did in grade 10, right? And let's do some interesting ones. Whoa, what's wrong, dear? What's wrong? You're tired? Okay. So on the very first page, we talked about the properties of radicals very little bit. You've seen the product. The same is true for division. So root 20 over 49, what can we do with that? If I go back to this. Whee! Right? We can write it as two separate radicals. They don't have to be under the same radical. Why might I want to do that in this question? Why would I want to write this as two separate radicals? What's so special about one of those numbers? Perfect square. 49 is a perfect square. So if I separate this into two separate radicals, I can actually get a beautiful number for root 49. What does that equal? Just 7. So what happens with our 7s? Do they cancel out? Because essentially the 7 that's a coefficient, you can write that as 7 over 1, right? It's on the numerator. And so they will cancel out. Is root 20 fully simplified though? No, we can write that as a product of root what times root what? Which 4 times 5. Notice how I like to put my perfect square first because that's the one that we're pulling out. Which equals square root of 4 is 2. 2 root 5. Okay, so let's have some fun. Let's play with variables. Okay. If you were in AP last year, then you would have worked with the variables. If you weren't, you didn't. Okay. So, square root of x squared. Let's start with the very basic. What is the square root of x squared? Why? Because the exponent and the index, it's essentially like they cancel out because they're opposite operations, right? And so what happens here is essentially, do you remember changing your radicals into exponents in grade 10? Power over root? So it was like the exponent was 2 divided by the index of 2. You remember that? Like if you had the cubic root of x to the 7, that's the same thing as x to the power of what divided by what? 3 over 7 or 7 over 3? You know it, you're just not saying it. The quietest class award goes to 7 over 3. Okay, so power over root. I used to always call it flower power. Like, you know, Mario Brothers. Do you ever play that? Is that like an old game now? Like, that was my childhood. Like, first Nintendo, that was me. Those are good days. So, right? The power is over the roots. The roots are always on the bottom. So 7 divided by 3. So same idea here. Our power is 2, our index is 2. What's 2 divided by 2? It's 1. And so that's another way to look at this. Okay? So we're dividing our power by our index. So when we want to actually pull out, because we're dividing power by index, we always need a multiple of our index in order to actually square root it or pull it out or divide it. So x cubed, right now, we can't break that down. It's going to be a decimal, right? You could write that as x to the power of 1.5. But that's not simplifying the radical. So what we want to do is we want to break it into a product of where one of them we can square root. So we can square root x squared, right? Agreed with that? And how many x's are left over? 1. We're essentially break it into the largest multiple of 2. The largest number that I can divide by the index. Well, from 3, it'd be 2. And then 1 left over. What's the square root of x squared? X. So, and then can you square root? Can you simplify that? No. So x root x. That's how you'd simplify that as a radical. Are you with me or did I lose you? Anyone? So we're breaking it into the largest multiple of 3. What's the next question like? Is it like jump right into? Okay, good. X to the 7. So let's look at x to the 7. Let's try this guy before we like make things interesting. So x to the 7, what's the largest multiple of 2 we can make out of the number 7? Like we want to split up into 2 numbers, right? A product. Yeah? Yeah, what is it? I heard you say it. Largest multiple of 2. The number's 1 to 7. 6. X to the 6. And how many x's left over? 1 x left over. Okay, would you agree that x to the 6 times x is equal to x to the 7? Yeah. Can we square root x to the 6? Yeah. What is that equal to? X to the power of what? 3. We take the index divided by, take the power divided by your index. Or think of it this way. x to the 6 as x cubed to the power of 2, or x cubed times x cubed. And the opposite operations cancel out, the square and the square root, so you're just left with x cubed. It's another way to look at it. Okay, so x cubed root x is how we simplify that guy. All right. I want to come back to h, because I just threw in a 7th power like it's no big deal, but it kind of is a big deal. So we're going to come back to h later and go to I. So let's try simplifying this guy. So first let's talk about 63. What is the largest perfect square that goes into 63? If you're not sure, we can divide. 63, so 49. It has to be at least as big, so obviously not that one. 36, no. Then there's 25, then there's 16. 9, thank you. 9 times 7, right? 9 times 7. So I'm going to put 9 and then 7 over here, because 9 times 7 gives you 63. We can square root 9. We can't square root 7. So we're breaking out one set of brackets is going to be all the things we can actually square root, and the second is what we can't simplify, what we can't square root. So n to the 7th, how am I going to break up n to the 7th? What's the largest, because its index is 2, largest multiple of 2 between 1 and 7? N to the 6. And how many n's left over? 1. How about p to the 4? Can you square root p to the 4? Yeah, as long as it's even, we can square root it. As long as it's even. So that can go in the first set of brackets. So everything in the first set is what we can actually square root. Do you see how this product equals this still? All right, square root of 9. 3. Ooh, what is that? I don't know. Oh, wait. 3. Square root of n to the 6. N cubed, we just cut it in half, divided by the index. Square root of p to the 4, p squared, and then we're left with root 7n. Not so bad? Or so bad? Can you try, Jay? Sounded fun. Where are you, Jay? Okay, give Jay a try before we venture into fifth roots and cubic roots. Oh, we didn't do any cubic roots. Oh, that's okay. Okay. I think I'm just going to change the 7th root one first. Yeah, let's just change it. Okay, this is already good. Can we change the letter H? I did 108, right? It's okay. Was it 108 that I chose?
Yeah.
Okay, so cubic root of 108, don't cheat, m to the 7th. What if it's a perfect cube? And we want to simplify it. So a perfect cube. So if we're dealing with perfect cubes, we want the largest perfect cube for 108, largest perfect cube that goes into 108. So our perfect cubes, if you're not sure, you could use the little quick way. Y equals x to the power of 3, and then go to your table. And we made that table up earlier, but, right, 1 cubed is 1, 2 cubed is 8, 3 cubed is 27, and 4 cubed is 64. And so we want to find the largest perfect cubed that goes into 108. So our perfect cubes are 1, 8, that's 2 cubed, 3 cubed is 27, 64, right? Those are our perfect cubes. So what's the largest one that goes into 108? Surprise, surprise. Okay, 27 times what? 4. So we're going to split up into 2 brackets. 27 times 4. Can you cubic root 4? Don't be deceived. You're so used to square rooting it. It's a perfect cube. You can't cubic root 4. Okay, m to the 7. So we want to split up m to the 7 in the largest multiple of 3. The largest multiple of 3. So 6 in this case would be 6. And how many left over? 1m left over. Because in order to cubic root it, I have to go power divided by index. Right? We're dividing it by our index. And so we want the largest multiple of the index that we can break it into. All right, what is the cubic root of 27? Nope. 3? Yeah. But you're on the right track. 3, cubic root of m to the 6. M to the 2. The cubic root of m to the 6 is m squared. 6 divided by 3. Power over index. And then this is what's left over. Sound good? Good old perfect cubes. So let's do perfect fifth question. All right. So first of all, let's figure out what our perfect fifths are. I'll write a little note down here. 1 to the power of 5 is 1. Well, we never use that one, but I'll write it down anyways. What's 2 to the power of 5? You can use your calculators. I will not judge you. 32. 3 to the power of 5.
243.
243. Too big, right? We only have one option in simplifying, really. So if we want to simplify this further, we want to split up into 2 sets. Numbers we can take the fifth root of, and including variables, and ones that we can't. So 64, what do we want to break it into? Which one of these will go into 64? 32 times what? 32 times 2. Okay, now how am I going to split up x to the power of 11? We want the largest multiple of what? 5, the index. So 10, you're going to use 10. Largest multiple of 5, we can do x to the 10. And then, how many x's left over? 1. Okay, y to the 17. Largest multiple of 5. 15. And how many y's left over? 2. Should almost move this all over. Nope, that's not going to work. Just erase this guy. Put the 5 in here. Okay, there you go. All right, so we have 3x times, we can take the fifth root of all of this. All of this we can take the fifth root. And then this guy we can't, so we'll leave him left over. What is the fifth root of 32? What is the fifth root of 32? If 2 to the power of 5 is 32, then the fifth root of 32 is 2. 2. Okay? What's the fifth root of x to the 10? Fifth root of x to the 10. X squared. 10 divided by power divided by your index. What is the fifth root of y to the 15? Y cubed. And so this simplifies. We can do one more thing. Multiply it with the 3x. So it gives us 6 x cubed, y cubed, fifth root of 2xy squared. Isn't this fun? I don't get out much these days. All right. So one more, and we'll call it a lesson. Now we're doing with what? Perfect fours. So 1 to the 4 is 1. 2 to the 4 is 16. 3 to the 4. I think it's 81. You're squaring it twice. Perfect fours you square twice. So 3 squared is 9. 9 squared is 81. 4 to the 4. Well, 4 squared is 16. 16 squared, 256. Okay, so those are our perfect fours. So we're going to simplify this guy. 162. Which one of these is a factor of 162? 81 times 2 will give you 162. Okay, so I'm going to go back up here. So we have our coefficient. We're still simplifying this though. So 4th root of something times 4th root of something. So you told me 81 times 2. Okay, how are we splitting up x to the 9? Largest multiple of 4, so x to the 8, and 1x left over. How are we splitting up y to the 12? Just y to the 12. Is it a multiple of 4? Yeah, so we can 4th root that. So 2xy stays here. Let's take the 4th root of this guy. 4th root of 81 is 3, right? Because 3 to the 4 is 81, the 4th root of 81 is 3. 4th root of x to the 8. X squared. 4th root of y to the 12. Y cubed. And so one more step. Multiply these guys. 6x cubed y 4. 4th root of 2x. Alright. That's it. So lesson for today. It's page, the homework, page 278 to 281, numbers 1 to 6.